So let's look at section 1.2, and that's a terrible 1.2. Try that again. And what we want to start off with are some representations of complex numbers. Okay, so the first thing is simply if we think of them as an XY pair, then we can go to the Cartesian plane, and here's where we usually put X and here's where we usually put Y. Now in this case, what we're going to do is call this the real axis, and then the Y, since we think of Z equal X plus IY, this is imaginary. And so, XY is just some point here, and this would be some Z equal X plus IY. Now, if we want to talk about then the size of a complex number, well, that gets a little more difficult than with real numbers, because real numbers are what we call well ordered, in that if you give me two real numbers, one's either greater than, less than, or equal to the other, and so I can always set them up in some sort of ordering from smallest to biggest. But once you go to a Cartesian plane, well, no, you can't really do that. Now we can still talk about the size or the absolute value of something, and so we can talk about the absolute value. Okay, so that's one term. Norm, we can also use that term, or we can use modulus of Z. And in that case, we would say absolute value of Z. Now, we could also call that the norm of Z. Now, it's possible that if we're using the term norm a lot, we might use two lines on each side instead of one. But the absolute value of Z is simply the Euclidean distance from 0, 0 here out to the point. So it's just like regular Cartesian coordinates, x squared plus y squared. All right, so you can think of it as a right triangle. That distance is x, that distance is y, and we have the components x squared plus y squared. Now, we'll also, for that modulus, we can also use the letter r. So x squared plus y squared. And so this is, when you see this is getting into polar coordinates. Okay, so so we have that. Now, similar with polar coordinates and all that, if I think of that right triangle and there's theta, then, and here's r, is that distance there, then what we see is that we can write x equals r cosine theta, and y equals r sine theta. Okay, so if we know theta here, we can do that. Well, so that gives us another representation of z. So, we had the usual rectangular representation, x plus iy, but we can actually go to polar and substitute these items in here for x and y, so we can say this is z equals, now I'm going to factor out the r, so write that as r cosine theta plus I sine theta, and this is a polar form. Okay, and here that theta is called the argument of z. Now the thing is, arg z, let's see, I'm looking at the text here while I'm doing this, trying to see, do they I'm just looking to see if they yeah, I don't see that they use any shorter notation. That's kind of long to say, so theta equals arg z. I'll put you on pause. My grandson just came in. Okay, I'm back. Of course, when you think of angles in the Cartesian coordinate system, arg z is not unique, right? In that, if I'm talking about this complex number here, z, then I could say, oh, well, that's theta, whatever that is, and that'll be a number between 0 and pi over 2. But I could also say that is theta, which will be a number greater than 2 pi, but less than 2 pi plus pi over 2. Or for that matter, I can go the other direction and start down here, go all the way over there, and there's theta, and in that case, theta is negative. So, there are lots of different values of theta that I can use. I don't think we're going to, in this course, be able to get to, where we worry about what we'll call the principal argument and that sort of thing. But just realize what we use for theta doesn't necessarily have to be unique. If you want to specify that theta has to be between, say, 0 and 2 pi, you can do that, or you can specify that it's between, say, minus pi and pi, those types of things. But that is arg z. Okay, so we have at this point 3 representations. If I come back, we had the original. I can just talk about x and y, the real part x, the imaginary part y, and just talk about that ordered pair. And I think your text is calling this the formal representation. And then we have a rectangular form, x plus iy. We've got our polar form, r times cosine theta plus I sine theta. Any of those will work. Now, we have a most amazing relationship. We have Eulers formula. And so Typically, this is also called the polar form because it really doesn't matter. You know, we're talking about the modulus and the argument when we use this formula. But we have that e to the I theta is equal to cosine theta plus I sine theta. Okay. Now this is, you know, the way I usually prove this sort of thing is from a calculus 2 concept called the Taylor series. And so Taylor series are infinite polynomials that can be used to represent functions. And so, for instance, cosine of theta can be represented as 1 minus theta squared over 2 plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial plus, and it just follows this pattern, so plus theta to the 8th over 8 factorial and so forth. Similarly, sine theta and dot, dot, dot. So that just keeps going. Sine theta is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus theta to the 9th over 9 factorial, and so on. And I'm not going to do it here, but you know, you could go to something like Desmos and plot cosine of x and plot, you know, this polynomial here out very far, you know, keep going out to maybe the 20th power or something like that, and look at how well the functions agree, and you'll see that they agree quite well for a while, and then because if you stop either of these polynomials at some point, you won't get total agreement by any means, but it'll look pretty good for quite a while if you go out far enough on the powers of theta or x, whatever you use. Now then, e to the theta is equal to 1 plus theta squared over 2 plus theta cubed over 3 factorial plus theta to the 4th over 4 factorial plus theta to the 5th over 5 factorial, and so on. Now, if you look at this, you know, you notice that, yeah, all the even terms look very similar to the cosine, and all the odd powered terms look very similar to the sine, but not exactly. But now let's look at e to the I theta. Well, so to evaluate that, just put in I theta everywhere you see a theta, and so that's 1 plus I theta plus I theta squared over 2 plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial plus dot, dot, dot. So we just make that substitution. Now note, I squared is equal to -1. I cubed is equal to -I then, because I'll take -1 times I. And then I to the fourth is equal to 1, but that means I to the fifth is equal to I, and it starts all over again. So I to the sixth will be -1, and so forth. So if I use that, then my e to the I theta is equal to 1 plus I theta, and then minus theta squared over 2. And then I'll get I cubed there, so that'll be a minus I times theta cubed over 3 factorial. I to the fourth is 1, so I'll get plus theta to the fourth over 4 factorial. Then I'll get my plus I theta to the fifth over 5 factorial. And then minus theta to the sixth over 6 factorial, and so on. Now, actually, this takes a bit of higher level machinery to know that you can actually do this with a, because this is an infinite series that just keeps going forever. So in general, you just can't willy-nilly rearrange terms. But in this case, we'll just have to take, somebody's word for it for our class. But we can rearrange these, so I'm going to rearrange the even powers first. So this is plus 1 plus, oops, not plus, but minus. Minus theta squared over 2 plus theta to the fourth over 4 factorial, and then minus theta to the sixth over 6 factorial, and then it'll keep going and be a plus theta to the eighth over 8 factorial and so forth. And then plus, now the odd terms all have an I in front of them, so I'm going to factor out the I, and I get theta, then minus theta cubed over 3 factorial, and then plus theta to the fifth over 5 factorial, then it'll be minus theta to the seventh over 7 factorial, and plus dot, 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 like that. And so, looking back, we see then that first set is indeed the cosine, and the second set of, the second infinite polynomial is I times the sine, and so there we have cosine theta plus I sine theta. Okay, so that's Euler's formula. So another way to represent z in polar form would be RE to the I theta. And, but that's the same as R times cosine theta plus I sine theta. Okay, but we could also just write that as x plus IY. So there we have lots of different forms for our variables, complex variables. And actually, I've always loved this one, because using Euler's formula, it can often actually make coming up with trig identities much easier, just by equating parts and so forth. So, so for instance, what if I, according to this, then, if I want RE to the I2 theta, right, that's equal to R times well, and actually I don't really need the r, but cosine 2 theta plus I sine 2 theta. Okay, so we've got that, but it's also true that, let's get rid of the r's here. It's also true, of course, that e to the I 2 theta is just e to the I theta times e to the I theta. And so that's cosine theta plus I sine theta squared. And so that is cosine squared theta. Now for this term, when we square it, we'll get I squared, which is -1 sine squared. So this is minus sine squared theta. And then our imaginary will be plus 2I sine theta cosine theta. And so what that tells me is equating real and imaginary portions here, that cosine 2 theta is equal to cosine squared theta minus sine squared theta, and sine 2 theta is equal to 2 sine theta cosine theta. I love complex variables that way. Okay, so this Eulers formula using the exponential representation here for our polar form, it's awesome. I can come up with these trig identities quite easily using some algebra. Okay, so there are some various forms that we'll be using for complex numbers. So we'll put an end to this video.